What up, guys? Welcome back to the second part of the 3.4 video. This is functions or transformation of functions. So let's kick it. This part is vertical and horizontal compressions and stretches. All right, compressions and stretches. Now, this part is easy, yet it has a little tiny twist to it. All right, it has a little twist that if you really don't pay attention, it's going to catch you and it's going to make it seem very difficult. All right, so listen closely. The first thing I want to say is when we're talking about vertical, compressions and stretches, this is what I literally want you to imagine. The vertical compression is when we are creating or squishing, right? Squishing just like this image right here. We're squishing our function. So look at this red function right here. Imagine if you were to vertically compress it, wouldn't the arms of this function flatten out or get wider? Yes, they would. Now, the more strength you put, the more vertical compression you create, the more the graph will open up, okay? The more it get wider. Now, I want you now to think about vertical stretch. Imagine if you were to grab the graph and stretch it up and down, all right? I want you again to look at the red function as the parent graph. This is the starting graph, the red one. What would happen if you start stretching it vertically? Hopefully you agree with me that the arms will start to go inwards. If you stretch this vertically, it'll start to go inwards, all right? Imagine that you had a balloon, right? Imagine that there's a balloon and the balloon doesn't really have air. It's a flat balloon. Imagine you have this image of a parabola on the balloon. So it's a latex balloon. If you were to pull this balloon that way and that way, wouldn't the arms become more narrow, right? Wouldn't it become like the green one and then the blue one? Yes, it would. If you don't agree with me, boo to you. All right, so that is what I want you to literally think about, vertically stretching and vertically compressing. The next thing I want to talk about is the following. I'm going to go to the next slide before we take any notes in our little worksheet. In the next slide, we literally have the same images, same exact images, but now it's horizontal. I literally grabbed my images and I rotated them so the change is horizontal. When I talk about horizontal stretch, this is what's going to happen to my function. And when I talk about horizontal compression, this is what's going to happen to my function. Now, here's the part that I was warning you guys about that might seem a little tricky. Once again, these are the same images as before, same exact images. Look, I'm going to go really quick, back and forth, so you could see that these are the same images. What I want you to understand is that if I grab the red parent function, and I do a horizontal stretch like the one right here, wouldn't my arms open up and make the shape wider? Yes, it would. Now, the part that makes this a little interesting is that a horizontal stretch, which is this right here, wouldn't that be equivalent to a vertical compression? Which means if we grab this function and squish it like this, vertical compression, and it is true. A horizontal stretch causes the same thing as a vertical compression. So that is something that you want to keep in the back of your mind. Let's move down here. Right now we have the parent graph, the red one. What would it look like if we start pushing it inwards? Wouldn't it turn into the green one and then the blue one? And then obviously the more and more you push horizontally from each side, the more narrow it's going to get, the skinnier it's going to get. Well, hopefully you could tell that a horizontal compression, like the one that I'm showing you with my arrows, it is the same thing as a vertical stretch. If I were to grab the red one and stretch this vertically, it'll start to get thinner and thinner. Okay, so why does it matter if these two things if horizontal and vertical stretches and compressions pretty much do the same thing yet opposite? Where does it make the difference? Where does it make the difference? Well, I'm about to tell you right now. Look where K is multiplying right now. By the way, compressions and stretches are created by multiplication. When we did addition and subtraction, that's when we moved it up, down, side to side. So adding and subtracting creates a move, a slide of the function, a slide of the graph, where multiplication will create a stretch or a compression. Now, the difference is multiplying inside versus multiplying outside. All right, so going back to the notes, check it out. In your vertical part of your notes, what I want you to write is this piece right here, where k is located outside of f of x, our parent function f of x. Let's see what happens when we decide to multiply a parent function by a number outside of the parent graph. Let's go ahead and jump to Desmos. Here's my parent graph. I'm going to be utilizing the quadratic function, the parabola. And what I'm going to do is I am going to multiply this entire thing. So I'm going to multiply outside. So I'm putting parentheses just to show that I'm multiplying my entire parent function. And my parent function is x to the second power. So I'm putting it in parentheses, and I'm going to put my number outside of the parentheses to show you that I'm multiplying outside of the parentheses. Now, let's see what happens. It's going to be the color red. So let's see how the red changes. Let's say I want to put the number, let's start with easy numbers, 3. Ooh, okay. What happens if it becomes larger than 3, like 31? Ooh, it becomes more narrow. Or what happens if it's 314? Very, very narrow, right? So you can see that it still has a shape of a U, but it's just becoming more and more narrow as the as the numbers become larger. So what can we say it's happening here? We can say that the larger our number is that we're multiplying outside, what's happening is, and remember, I want to remind you, we are thinking outside, right? And outside means, let me show you here with the little marker. Since we are multiplying to the f of x, that means that we are multiplying to the y. So you got to think vertical. Y is our vertical numbers. Y is our vertical numbers. Y is our vertical numbers. So what we're about to say right now, it's a vertical something. So for the black to become the red and become more and more and more narrow like this, that means that we are doing a vertical what? What do you think it's happening? Are we doing a vertical stretch like this to become narrow? Or are we squishing it like that to become narrow? Well, the answer is we are stretching it vertically. That's what's going to make it become thinner and more narrow. The higher the number, the more power it is that we're pulling this vertically, right? We're stretching it. Now, something that I can do is I'm going to go ahead and delete this 14, and I'm going to put the letter K so you guys could see it as it is in the whatchamacallit, in the slideshow. And I created it as a slider. So it asked me, Desmos asked me if I want to do a slider. So yes. So you could see what's going to happen with my parent graph as I multiply it with a number that's greater and greater and greater each time. It becomes more and more vertically stretched. Okay, more and more vertically stretched. Now, the next question is, what happens if I go the other way? What happens here at 0? Well, at 0, it just becomes a flat line because, and if you're wondering, zoom out. You can see it if you zoom out. No, it's a flat line because remember that 0 makes everything go away. So we got rid of our graph. So we don't really want k to be 0. We don't want k to be 0. So let me keep going to the left and see what happens. Ooh, okay. So I see here that we're now upside down. So I don't want you guys to worry about going upside down. I don't want you guys to focus on the on those type of numbers. What I want you guys to think about is, I know that numbers that are greater than 1, like these here, 45, makes a, here goes for your notes. When the numbers are greater than 1, we're going to be vertically stretching by a factor of k. So go ahead and pause it right now and write it down. Now, what happens when the numbers are less than 1? But I'm not talking about negative numbers. I'm talking about fractions, people, fractions. What happens when we multiply by fractions? So we already know that if we multiply by a number, once again, like the number 6, we get thinner and more narrower. But I want to get wider than the black parent graph. So what I'm going to do is I'm going to see what happens when I multiply by a decimal, like 0.75. Ooh, do you notice how from black to red, it gets wider? So let me go ahead and do another one where my multiplication is by a number smaller than 0.75, 0.25 maybe. Ooh, look, it's getting more wide. Let's do another one. Let's go ahead and do y equals, let's do parentheses, x squared, close my parentheses, and let's do an even smaller number, a smaller decimal, 0. Let's just call it 0.10, 0.12, doesn't matter. So this does the exact opposite. As my decimal numbers get smaller and smaller, my graph gets wider and wider. Okay, wider and wider. So it has to be fractional, by the way. It has to be a decimal number for it to be wider than the original one here. As you can see, all the ones that are not flashing right now are wider than the one here. Cool. So let's go ahead and go to our notes and talk about what we just noticed. Here it is. If k is a number between 0 and 1, meaning decimal numbers, the parent function will vertically compress. It's going to get wider, vertically compressed by a factor of k. And that's just a little pretty lingo that we use, by a factor of k, whatever number it is that we're multiplying by. All right. Okay. Now, moving on to our notes for the horizontal compression. Now, for the horizontal compression, this is what I want you to write. I want you to go ahead to write the parent function f of x, but we are now multiplying inside of the parentheses. That means we're multiplying directly to the x. We're literally multiplying directly to the x. That means what's happening now has to be called a horizontal something. Okay, so the lesson that the slide that we just did right now was either a vertical stretch or a vertical compression, a vertical stretch or a vertical compression. All right, now let's go ahead and see what happens when we multiply inside of this parentheses. And when we talk about inside of the parentheses, that means that we have to boot out the power of 2. Very important what I just said. You have to boot out the power of 2. Let's put it outside of the parentheses. So this is actually done properly because I want to do it straight to the x. I don't want to do it to the x to the second power. I want to do it straight to the x. Let me change the color here so they all look different. All right, so I got my parent function right here, the black one. Let me hide these. Let's go ahead and see what happens here. Now, just a little recap. If I multiply 5 outside, yes, we already said that it's going to get stretched, right? Vertically stretched. It's vertical because of that side of the parentheses. Let's see what happens here in the purple one when I multiply that 5 inside. 5 inside. Ooh, what happened here? Do you guys notice that this has the same effect? I don't want to say it lands on top of each other. The purple and the red do not land on top of each other. But doesn't it have the same effect? Doesn't it make the parent graph, aka the black one, more narrow? It does. But listen to what I'm about to tell you right now. The red one is called a vertical stretch by a factor of 5. That's what you would say for the red one, a vertical stretch by a factor of 5. Now, horizontally, we cannot say that this is a horizontal stretch, because if you imagine grabbing this arm right here and pulling it to the left, and then this arm right here and pulling it to the right, that would make your graph look fatter or wider. What we want is to push these two black arms right here. We want to push them inwards. So this is called a horizontal compression. So let's recap what is similar. A horizontal compression, or pushing this function right here, pushing their sides together, will create the same thing as a vertical stretch. It'll create the same effect as a vertical stretch. So let's do that. Boom. If k is a number that's more than 1, like 5, the one that I just used right now, the parent function is going to be horizontally compressed. It's going to be horizontally compressed. Now, if you're taking notes right now, this is what you can do. You can go ahead and grab your pencil and give yourself a little sketch of a parent graph, and then grab another pencil, a color pencil, or a different lighter shade with your lead pencil, a lighter shade, and do this. Show that it gets narrower. Now, for this to become narrower, you want to horizontally push the sides. You want to push the sides in, which we call that a horizontal compression. Okay. Again, remember, we need to keep the word horizontal in this slide because we are multiplying inside straight to the x. All right. The next one. Let's see what happens when our 5 actually is a 0.5, like we did before. Boom. All right, so we already talked about this before. We already talked about, let me actually make it, yeah, let me make it 0.5. Let me make it a little bit wider. All right, so I'm sorry, 0.05. So we already talked about later before that vertically, this is called a vertical compression, vertical, because for the black one to become the red one, in a vertical sense, I need to squish it. I need to squish it, the top and the bottom. All right. Imagine that drawing that I had, that picture that I had, compressing that spring. All right, cool. So let's go ahead and grab this number here and make it the same thing as 0.05 and see what happens inside of the parentheses. So multiplying outside creates a vertical thing and multiplying inside creates a horizontal thing. Let's see what happens. All right, so what happened? So the red one is wider than the black one, than the original one. The red one is wider than the parent graph. Is the purple also wider than the parent graph? It is. So the same thing happened. Obviously, the purple one happened a lot more. It happened a lot more, but algebra 2, that's when you're going to learn where it was that, or why it was that it was a lot more, okay? What makes that big jump? What we're only worrying about in algebra 1 is how do we name it? How do we name what just happened right here? Here it's called a vertical compression because vertically we squished the parent graph to become the red one. Now, here it's a horizontal what? What can we do horizontally to the parent graph, the black one, to become the purple one? Well, we need to grab those arms and we need to pull them out. We need to pull these arms out so they can extend out, get wider like the purple one. And that is called a horizontal stretch. Okay, so let's go ahead and talk about it. If A, or whatever number we're multiplying in there, is a number that's from 0 to 1 or a decimal number, what's going to happen is we're going to get a horizontal stretch. We're going to get a horizontal stretch. Once again, if you're taking notes right now, this is what's going to happen. Okay, that's just my little ghetto sketch. And you could see that instead of horizontally compressing, we are going to grab those arms of our original function, our parent function, and stretch them out so they can become the other one. And that is what happens. That's it. As simple as that. Now, obviously, we haven't even done practice problems. So if you're wondering, I don't know if I'm getting this, well, you've just been exposed to a lot of information without really any practice problems. So let's do this right here. It's a little review. I don't even want to call it practice. It's more of a review. Let's see if you're understanding it. Let's go ahead and recap. All right. So for the following functions, I want you to state whether the independent or the dependent variables are being transformed. And remember, independent is your x because the x doesn't need the y. The y is the one that needs the x. And your dependent is your y. And then after that, go ahead and tell me what the transformation is. All right. So our dependent variable is being transformed and describe the transformation. It's supposed to say the transformation. I'm sure that I have something here hidden because the transformation. Boom. There we go. All right, cool. So describe the transformation. All right, so for A, let's go ahead and do A together. A, I can tell, so I'm just gonna ask myself first, am I multiplying to the X or am I multiplying to the Y? Well, this right here is considered, all of this is considered my parent graph. This parent graph is G of X. Now, if you're wondering, well, this one says G of X, this one has a letter F, this one has a letter H, that one has the letter G. Don't worry, remember that at one point I taught you guys that this is just the way that we name functions, just like how there are several kids in your classroom. We all need different names so we can kind of distinguish who is who. So that's it. That's just a name to it. So this parent function G, the G function, this is happening to it. All right. So what I want to remind you is that the G of X is the same thing as saying Y. So we're multiplying straight to the Y. This right here. And what is the Y? What does Y tell us? Well, Y tells us that something is being done vertically because Y values are up and down numbers. All right. So first part of my question is, what am I affecting? I am affecting the dependent, the Y. And what actually is the transformation that's happening? Well, now I go to the second part and ask myself, look at this number. Is this number greater than 1 or is it a fractional number? The answer is it's a fractional number. That means we are going to get a wider graph. Whenever we have a fractional number, we get a wider graph. Okay, so this is what's happening. This is our original. Something is happening vertically. Something's happening vertically. and it's causing our graph to become wider. What happens vertically for our graph to become wider? Well, what needs to happen vertically is for you to grab it up here and down here and squish it, right? You need to compress it. You need to compress this so the arms of the parent function, the black ink right here, widen out to become the red one. How do we write that? Here it is. Here's how the professional way of writing it. G of x is being vertically compressed by a factor of 0.5. That's it. Moving on to B. I want you to try to pause it right now and try to do it on your own. I'm gonna go a little bit quicker now because it's the same thing, different numbers. All right, here we go. Now, something we need to realize is that we are multiplying straight to the x. We are multiplying straight to the x. That means that we are affecting the independent variable. Independent variable is the x variable. That means that the movement or the thing that is happening is horizontal. It's a horizontal thing that's happening. The next thing I want to look at is the number. What type of number is this? Is it a number greater than 1? And that number is similar to A, is a fractional number. So what's happening is the same exact thing is happening from A to B, where our parent graph is becoming wider. So how do we say that horizontally, what do we say happened when horizontally it became wider? Well, for it to be horizontally wider, we need to grab these arms and pull them out. So that's called a stretch. Again, look at my arrows. The arrows that I'm creating here, the last two that I did, they're horizontal arrows that go side to side. The ones that we did before are going up and down, vertical arrows. So be careful. Remember the difference, vertical arrows and horizontal arrows. Careful. And I meant to say horizontal here, vertical here. All right, so what happened here was a stretch, a horizontal stretch. By how much? Well, by that number that's right there. That's easy as that. The parent function f of x is being horizontally stretched by a factor of 0.75. All right, if you did not try B on your own, again, I try to encourage you guys to try C and D on your own. Pause it right now and do it. You got this. All right, let's go ahead and talk about it. What are we multiplying the 3 by? Are we multiplying it by our x or by our y? And hopefully you could see that we are outside of the parentheses, meaning we are affecting directly the y value. Our y values are the numbers that go up and down, meaning vertically. So something vertical is going to happen. The next thing that I'm going to say is, I'm going to go ahead and draw this. I want to look at the number. This is the number 3. And we saw that with the number 3, our graph stretches, or it becomes, sorry, I don't want to say stretches. It becomes narrower. So it becomes narrower. It goes from the black parent graph to the red one. So what has to happen vertically for you to go from black parent graph to the red one? Well, you need to do a stretch. You need to grab, imagine that this was, again, like a balloon type of thing. And then you stretch that way and you stretch that way. So the black arms of this function stretch themselves inwards, okay? So that is called a vertical stretch. By how much? A factor of 3, okay? Moving on to the last one, we could see that we are again multiplying inside right to the x, just like how we did here for B. We're multiplying to the x, and x, and our x numbers are horizontal numbers. So that means that something is happening horizontal. What is happening horizontal? Well, oh wait, I was supposed to, I'm supposed to box in x because that is what we're affecting. And then I'm going to underline the number. The number tells us what happened to the graph. Boom. That number is less than 1. So my parent graph, what's going to happen is, since it's less than 1, it's going to widen. It's going to widen. As you guys could see from the practices that we've done, we've become wider once, twice, and now 3 times, and only became narrow 1. All right, so what happens horizontally? So what happens horizontally for these arms to become wider? This is very, very similar or identical to B, right? Because we have to grab these arms and pull them that way. That is called a horizontal stretch. So here we have a horizontal stretch by a factor of 0.83. Okay, that's it, y'all. As simple as that. This is your horizontal and vertical stretches and compressions. Stay tuned for the last piece. Peace out.